I'm a program manager in the Windows Server division at Microsoft. And Bruce Worthington and I are going to tag team to talk you through some of the new power management features that we're developing for the next version of Windows Server, which is codenamed Windows Server 8. I'll talk a little bit as an introduction about why we think it continues to be important to invest in power management, and then talk a little bit about some work we're doing to create a more collaborative power management solution between the hardware and the software. Then Bruce will come up and talk about some really cool work his team's been doing on managing power in the memory subsystem. And he'll talk a little bit then about tuning and developing for power management or in a power aware way. Okay, so customers continue to tell us that power and cooling continue to be an important issue for them, and something that's top of mind, really. Some customers tell us that they're limited on the number of servers they can deploy into their data center based on the mains grid power that's available to them, or the cooling in their infrastructure is such that they can't really add more servers, and they have problems in that area. We're also starting to see, particularly in Europe, governments creating laws that require companies that have facilities that use more than a certain number of megawatts to purchase carbon credits in order to keep those facilities going. We're also seeing changes in the way that data centers are being designed. There's a big emphasis on cost of operation, and really power usage and power and cooling infrastructure is a key piece of that cost of operation. And we're even seeing some instances where one of the key design points for the data centers is the power footprint of the server. So all of this tells us that it's important that we keep providing features in a new version of Windows that makes the platform more power efficient and saves power and cooling infrastructure in the data center. This slide is supposed to illustrate how we measure success, release over release, on power efficiency. It's an old slide, and it's just for illustration, but this shows an OLTP workload, and we're measuring power efficiency for that workload. So on the x-axis is utilization. So each 10% increment of utilization, we measure the performance of the workload, and we also measure the power that's delivered. So we get a power efficiency plot at each utilization level. And this graph, lower is better, with power on the y-axis. So this graph shows Server 2008 R2 relative to Server 2003 SP2. We're not at the stage yet where we can do this for Windows Server 8. We're just finishing up with the development, and we're going to get into optimization next. But our goal would be to do the same testing across a wide set of standard benchmarks and Microsoft workloads to make sure that as we add these new features to the system, we're actually improving power efficiency, and we can measure that across important workloads. And really, saving a handful of watts here can have quite an impact, quite a significant impact on our customers. If we can save 5 or 10 watts on a server by adding a new power management feature, that can add up to a large saving across thousands or even tens of thousands of servers in a data center over the lifetime of the servers. We run these tests on the same platform, so we're doing an apples to apples comparison, and we'll try to do it before we release on the newest platform that's available. This is just a little bit of history of what we've done in the past with Windows Server Power Management. Back in 2002, 2003, power wasn't such a big deal. And our default behavior with Server 2003 when it was shipped was to be as performant as we could be. So we spread the work across the hardware. Since then, we've got a lot of feedback from customers that that's not the way that they would prefer to have the default behavior. They would prefer to have it be power efficient out of the box. So we made a change in Server 2008, and we moved to a default behavior which goes for power efficiency. We introduced a processor performance state management capability at that point. I'm going to talk a little bit more about that and what that is in the next few slides. In Server 2008 R2, we added another feature that consolidates work onto a fewer number of cores when the system's under low utilization, and puts the cores that are vacated of work into a low power state to save more power, and we called that core parking. So up until now, a lot of our features have been focused on the processor. We also added some management capabilities in Server 2008 R2, which would allow the operating system to discover a power meter on the system if one exists, and also a power budget capability if one exists. We also created a remote management interface using WMI that allows remote management software to connect to the system, and it can change the Windows power policy, or it can use the power meter, it can read the power meter, and it can also access and use the power budget capability. So these are all things we've done in the past, and we'll talk a bit today about some new stuff we're doing around collaborative power management and some stuff that Bruce has been doing around memory power management. Okay, collaborative power management. This slide kind of talks through the operation of the existing processor P-state management solution that we have in Windows. This was the feature that shipped on by default in Windows Server 2008. For those that don't know, P-states or performance states are software writable states in the processor where you can change the power usage and the performance capability of each logical processor by setting a performance state on the processor. Obviously, if you set a higher P state, you use more power, but you get more performance. You set a lower P state, you get less power, but you also have less performance capability. And the goal here is to try and only use the power that's required to deliver the performance that's needed. So the way this works is the firmware creates an ACPI table. That ACPI table describes all the performance states that are available on the system. At boot time, Windows picks up that table and then has the knowledge of the power usage and performance capability of each of the P states on the system. Windows goes through this continuous loop of calculating how much performance is needed for each of the logical processors for the next power management interval that we call the performance check interval. And that's really done based on how much work is going to be scheduled to that logical processor over that time. Understanding what the performance requirements are, Windows can then go look at the ACPI table that was passed and can try and figure out which of the performance states that's available for the logical processor delivers the required performance at the lowest power. Windows then selects the optimal P state from the list and then writes to the hardware to set that P state on the system. And that just continues. The idea being, as I said, to try and only use the power that's required on the processor to deliver the performance that's required. So this model continues to be supported in Windows Server 8. It's effective. It does improve power efficiency quite a lot. So the question is, what's wrong with that model? And really, we got some feedback from some of our hardware partners that model doesn't really allow the hardware to differentiate itself in with this type of operation. What we started to see was, hardware is very capable of doing power management as well, and what we started to see was that some of the hardware vendors started to create their own power policies, and the customer would then have the option to either set a power policy at the hardware level, at the firmware level, or set a policy at the Windows level. And the policies were typically exclusive, so typically if you set one, you couldn't use the other, and vice versa. So talking to partners about this, we believe that the right thing to do is to move to a more collaborative model, where both the hardware and the software work together in their own domains to innovate and differentiate, and both ultimately add to the power efficiency of the system. We had a first go at doing this back in Server 2008 R2. We worked with HP, and between the two companies, we created a firmware interface that allowed the operating system to calculate the desired performance and pass that down through the interface to the hardware, and that was measured in percentage of performance, percentage of frequency, and pass that down to the platform, and the platform then would decide how to control the hardware. This was a good first step. Our plan for Windows Server 8 was to improve this by creating a richer data interface, and also really one of our main goals was to try and make sure this became an industry standard so it could be more widely adopted across the industry. So what does the collaborative model look like today? Really, we needed a low latency communication transport to pass the information, and critically, we needed it to be a standards-based solution. It has to be low latency because these checks are being done by default every 50 milliseconds, so the data can be passed at a fairly high rate. We're currently working in the Advanced Configuration and Power Interface Forum, the ACPI forum, to create a communication transport that's low latency. The goal would be to make this a generic communication interface that can be used for multiple purposes, with the first purpose being to pass processor performance information across the interface. Bruce is going to talk about, as I said, about memory power management, and that's another usage model for this interface. So what does the new operation look like for processor power management with this new model in Windows Server 8? So in this model, the hardware no longer needs to pass the P-state details to the operating system. The operating system would advertise support for this new capability. The firmware would also offer support for the capability and would detect that the operating system has the support. Windows still creates the desired performance the same way as it's always done, but now rather than trying to write anything to the hardware, it passes the information through this new fast interconnect in the firmware. The firmware then detects that this information has been passed, and it goes and reads the information, and then it's completely up to the hardware how that performance is delivered. So the hardware can use the power controls on any of the components that it sees fit to deliver the desired performance. And so that could be another thing that the hardware can do at that stage is if, for example, if the utilization level is getting low and the power usage of the processors is going down, it could take advantage of that and possibly slow down the fans because there's not as much heat being dissipated, or change the power regulators to save more power. So really, it offers the hardware the option there to differentiate and innovate moving forward. Another advantage we have here is that the hardware and the software can keep in sync on what's going on in the system more. For example, if there's a power constraint on the system and the hardware can't deliver the desired performance that was requested by the operating system, it can provide that information back to Windows in a feedback loop. So it can send information back to tell what the actual delivered performance was, and it can indicate why it wasn't the requested performance. So with this model, Windows continues to calculate how much performance is required, but rather than Windows controlling the hardware, that is passed on down to the platform, and the platform decides how to deliver the performance in the most power efficient way. And that loop continues. I've just got a couple of slides now to talk about another collaborative power interface that we're introducing in Windows Server 8. And this is to help with power budgets. So power budgets are becoming more popular on servers, particularly on rack mount servers. And the idea with this is that the administrator could set a power budget on a system. There's multiple different reasons and scenarios why they might do that. But basically the way this works is that the admin would have some kind of management UI and would use that to identify a server and send a power budget down to that server. The hardware on the server controls the power budget. So what it typically does is once it gets the power budget, it will monitor the power meter and look for the power usage getting up close to the budget value. And if that happens, the hardware has to take action to reduce power usage on the machine to make sure that the power usage stays below the budget. And this feature really is intended to help keep operations more power efficient when there's a power constraint on the system and the hardware's having to throttle back on the components to stay within the budget. The feature is called logical processor idling. This was introduced in ACPI 4.0, so it's an existing standard. And the idea here is that typically when the hardware has to throttle back to stay within a budget, the first thing it's going to do is use the performance states. This graph here shows performance along the x-axis and power on the y-axis, and it's a typical type of result that we'll see in some of the testing we've been doing with this. So as you can see, performance states reduce power a lot, but you don't lose much performance. So we're going to assume that all of the performance states are going to be exhausted in this type of power budget situation before the platform would try to use any other type of throttle. Typically what might happen next is that the budget hardware might try to use throttle states, linear throttle states. These are not so power efficient. And what we see is you lose some power, but you lose a lot of performance. The idea with logical processor idling is we give another option here where instead of using throttle states, the system could use this ACPI 4.0 method called the PUR. And what it does is it sends a request to the operating system to ask the operating system to stop using a certain number of processor cores. And it passes a parameter where the parameter is the number of processor cores to stop. We give that as input into our core parking engine in Windows, and we'll always try to park at least as many cores as has been requested by this logical processor idling feature. And what we've seen is that we do see more power efficient behavior when we do that. So we still see that we can save the power, but we do it in a more power efficient way. If you look at one of the power points, the power lines along there, we get more performance at the same power level. So this offers another option to partners that are building power budget solutions that may want to try to use this feature rather than linear throttling. Okay, so just to recap on what I've said so far. We think collaborative power management will help. It will help simplify the power policy choice for the customer. When this is implemented on Windows Server 8 running on a system that supports it, by default, both the hardware and the software will default to using this policy if it's available. So the user won't have to make a decision between hardware or software-based policies. What it really does for the future, though, is it allows both the software and the hardware to continue to innovate in their own domains and add to the power efficiency of the system. Windows has really good knowledge of how much work is going to be scheduled to the processors. It has good knowledge of how the memory is going to be allocated amongst the physical devices, memory devices. It has good knowledge of how I/O is being sent out to devices. So the Windows can do a good job of trying to figure out how best to use those devices. The hardware, though, can do a much better job of innovating on potentially new interfaces to the components to allow new ways to more efficiently change the performance states. They can provide more useful performance states, better performance states. And they could also do things like be able to move quickly between the performance states, things that the operating system would find it hard to do. So really, this offers a model moving forward where everyone can feel like they're contributing to the power efficiency of the machine, which is what we want to do. Okay, so that's all I have. Bruce is going to come up now and talk about memory power management.
Alrighty, I'm Bruce Worthington. I'm a developer lead from the Windows Fundamentals team, and specifically I lead the guys that are looking at the energy efficiency of servers, clients, mobile systems, the whole range of SKUs. So, like Sean said, there's a particular feature that we've been spending a lot of time working on, and pretty much came out exactly like we hoped it would, so that's good. We think it's a success story. It remains to be seen exactly how it's going to play out on the latest and greatest hardware, but we're pretty psyched. So the basic idea is like Sean said, in previous releases and in the current release coming up, we spent a lot of time looking at processor power. That's been kind of the, forgive the phrase, it's the core piece of our power management so far. But in this release, we've stretched ourselves a bit and looked at other components in the system. So specifically, obviously, I'm going to be talking about memory. And if you look at some servers, and we've measured this by looking at the individual component powers, if you're running at a low utilization level, memory can actually be your number one cost when it comes to power. And so it's an area that's ripe for optimization. The hardware itself does some great things in regards to saving memory power. Memory has multiple power states it can get into, 6, 7, 8, 9. There's really a lot of flexibility there with different characteristics in terms of how much power it's saving versus how much exit latency there is in terms of a performance cost of hitting it when it's in that low power state and having to bring it back up to running state. So when the hardware detects lots of idle behavior, I mean, there's basically the whole system being idle. If you look at current systems, they will sometimes take advantage of that knowledge and actually drop everything into a self-refresh state in that one scenario. So they can go down, they don't usually go down all the way, but they'll take it down into sort of the top level of self-refresh, perhaps, if everything's idle. If there is some idle behavior, then they'll drop just a little ways into what's called CKE states. And those are very quick to get into and out of, but they only save you, maybe 10, 20, 30% of the power rather than, 50, 60, 70% of the power. So there's a real opportunity here for the OS and the hardware to collaborate, again, just in the same kind of way that Sean was talking about, so that we can tell the hardware, hey, we know this region of memory is not going to get very much activity because that's the way we've set it up. Why don't you go ahead and drop that guy down deep? And we'll get all the power savings we can out of it while maintaining the data. So we're going to maximize memory idle time and then drop it into the low power state, but be very conscious of the performance impact that could come from it. I was a perf guy before I was a power guy, and so I'm not looking for a huge I'm not looking for a huge performance hit just to get those few watts back. I want some serious benefit for my effort. And so while it's a little early to know whether or not memory cooling will be the default, like balanced mode is right now for processors, we do know that we can improve the energy efficiency of the system and do it in such a manner that perf has a small hit and power gets a nice benefit. And I'll be talking a bit about how we back off. Sorry, where's the laser? I'll be talking a bit about the back-off mechanisms we had, again, because we want to be very sensitive to that performance impact, and we want to get all the bang for the buck that we can. And when it's time to get out of the way, get out of the way. Okay, memory footprint, I guess it's also worth mentioning that it's not just the CPU that we try to be aware of, but also memory. And we've got a very, very small increase in footprint. This scales linearly with memory, so it's less than 1% regardless of how big your system is. So, like I mentioned before, self-refresh is this state. It's a fairly low state in terms of the power scale on memory, but it still maintains the contents. There is a lowest power state, obviously, where you're basically turning off the memory and lose your contents. That's not what we're doing for this release, but certainly it's something we're interested in. It's another power gain. And so looking forward to future releases, who knows? But there's still more opportunity is what I'm trying to say. We've got a little left on the table for us. Now, like I said, the exit latencies are an important piece of this because the deeper you go, the more costly it is to come back out, both in terms of power and the latency hit. For that first access, that has to take you all the way up. Okay, so when we break down all the work that we did, and it was pretty much you'd have to call it a large feature given the number of lines of code that were there. It was a big feature. It was a lot of work. It breaks up into two pieces. First of all, you have to be very careful where you allocate memory from. That is, you've got a range of places you could give somebody a page. Here's a physical page. Here's a physical page. Picking the right spot to give a specific physical page to a driver, to the OS, to an app is very important. It sets us up later for being able to cool. Now, the relocation is more the ongoing piece. We may not have allocated stuff we don't have crystal balls. We don't know that this page is going to be hotter than that page every time. And so we may have allocated a page and decide, afterwards, that probably wasn't the best place for it. Let's move it over here. So there's the allocation piece, there's the relocation piece, and both of these work together to create these cold and hot regions of memory. So we can take the cold regions and drop them down deep. For this release, we are using the NUMA node as sort of the boundaries in which we perform our memory cooling. We don't memory cool across NUMA nodes right now. Again, it's absolutely something that could be considered as a future optimization. There's some very cool things we could do. So again, there's something left on the table to continue this process. But right now, we stay within a NUMA node, and we manipulate the memory at that level. And so if you've got multiple NUMA nodes, obviously we're independently managing the memory across those different nodes. Right now, if you look at existing hardware, existing processors, the most likely candidate for a power region, if you will, within a NUMA node is the memory channel. So you can think it's got 2 or 3 DIMMs, maybe 4 even sitting on a memory channel, or they could have put an extender on there and put even more DIMMs. But the point is, that row of DIMMs, each one of those rows of DIMMs, is kind of a good target in terms of the power control. It just works out pretty well that way. But there's nothing that prevents it from being DIMMs or any other pairs of channels. All of that is possible. In fact, I don't really want to know exactly what the power region is. I just want the hardware to tell me, hey, I've got these regions, please manage them. And it can deal under the covers with how that's managed in terms of power rails, et cetera. So again, it's kind of like the processor thing, where we've taken an abstraction and we use it to say, here's some information, do the right thing with it. Both directions, hardware and software working together. So here's just an example, again, using that channel concept. If we had a couple CPUs, each of which has 3 channels, then we can take and manage these 3 channels in a memory management, in a memory cooling fashion, and those 3 memory cooling. But what do we need to know? We need to know how many regions there are, and we need to know the physical addresses. So I'm going to talk about that. So in a similar fashion, through ACPI, we feel like the topology of the system can be exposed that will allow us to do memory cooling. And in fact, we've prototyped and done this. We need that standard-based so that we can do it across the entire breadth of hardware. Anybody that wants to implement this, we want to support it. And we're working with the ACPI forum to get this in and push it through. Pretty much exactly like I said from the previous slide, we need to know the power regions, we need to know the physical addresses of the power regions, and we need to know what are the memory power states. Now, in this release, we're just going to a 2-level scheme. Either you're in the running state or you're in a low power state. And again, we leave it up to the hardware to decide which of those low power states to choose. In fact, it could even choose to use multiple ones and incorporate its own additional information. That's fine. We're going to give it some information about which regions are hot, which regions are cold, and then it can do a good job about making sure that the power is going to be dropped within those regions. The hardware controls that the last bullet is referring to, again, it's a bidirectional thing. So we're giving information to the hardware. The hardware gives information back to us dynamically as well. It can tell us, hey, this region is drawing that much power, or it has this many memory accesses per second, or whatever. It can give us information that we can then use to feed things like our backoff algorithms. If we're trying to cool this region, yet the power isn't dropping over here, there's something going on, we can back off. Obviously, the workload is not in good shape for us to be doing memory cooling in that environment, so we can back off. So again, that bidirectional communication is very important. It's working together. So we did write a lot of new code, but at the same time, we leveraged a lot of existing technology within the OS. This is not a huge thing glommed onto the side. This is working with the existing infrastructure and adding some pieces in multiple spots in the OS, and they all work together. So for example, the memory manager obviously made some changes in the memory manager. We made changes in the HAL. We made changes in several other places. And let's see, some of the things that were already in existence were the ability to actually track accesses to pages and figure out which pages are hot, which pages are cold. It wasn't used in that fashion, but they were tracking that kind of information for memory trimming and other situations like that. So we just leveraged that existing infrastructure. So what we use it for, I've listed several things here. So the new page allocations, like I talked about, allocation is the first piece you have to get right. Relocation, well, you got to decide how to move stuff around. And then providing the hints, we used existing channels that were made possible through the processor stuff. And then the backing off piece, again, getting that energy information back in one form or another so that we can do the right thing. So I've been using the terms hot and cold. I'm assuming you guys know what I mean by hot and cold. Either you're beating up the page or you're not. In fact, when I'm talking with my team, we talk about icy cold and we talk about lukewarm and we talk about blazing hot, right? Because it's not binary. But roughly, we categorize things as hot or cold. And cold is pretty darn cold. I mean, it really means it's not being accessed very much at all, most of the time 0. We keep historical information about each one of the pages so that as the workload changes over time, we keep up with that and we track with it. Now, there are some pages that we categorize not because of their access rates, but because of what they are. So, for example, non-page pool. You allocate it, you can't move it after that because there could be DMA going on, there could be all sorts of stuff going on. So there is a set of pages that we recognize that are very hard to relocate. Therefore, when we allocate them, we're very careful about where we allocate them and we keep track of it very closely. There's another set of pages that aren't necessarily unmovable, but it's hard to tell if they're hot or cold. There's specific OS metadata kinds of pages that just aren't tracked by the existing infrastructure that I was talking about before. It's just not there, and while we did take some of them and add them in by adding some additional information, there's still a small set left. It's a small set that are what we call untrackable. And so again, we can treat those pretty much in the same way as we treat non-page pool and say, we're just going to call those hot just to be safe. And so we're going to make sure that we allocate those very carefully. Power regions is basically the same thing. There's hot regions and cold regions. That's based entirely on how many memory accesses or how much energy is going into that whole power region. Sometimes, in fact, pretty much always on a server, I believe, there are pages that are allocated at boot that the OS may not even know about. They've been allocated for the purposes of the firmware, and it's perfectly fine that the OS doesn't know about that, except we kind of need to know that, because if those are pages that could be hot, and again, we're going to have to treat them that way because we don't know any better, well, we better know where they are so we can take the appropriate steps. So the primary goal, the thing that you've got to do if you're going to cool, is you've got to get the hot pages out of the cold regions. I mean, getting the cold pages out of the hot regions may be nice, but it's not really necessary in order to enable cooling. As long as you got the hot pages over there, I don't care if the rest of them are free or cold or whatever, just get all the hot pages over there. Now, you do have to shuffle the cold ones back sometime to make room for more hot pages to come over. So you do go both directions, but the basic idea is get the hot pages out of the cold channels. So Sean jokingly said, I only need this slide. I could do my entire piece of the talk just with this one slide because it kind of shows everything. So here we got a single NUMA node. It's got 2 power regions within it. So maybe it's 2 channels and 2 channels, or 1 channel and 1 channel, who cares? It's 2 power regions that are independently controllable by the hardware. And when we start off, we've got 1 hot and we've got 1 cold. And inside here, we've got some unmovable pages, we've got some hot pages and some cold pages. Okay, here's where we're starting from. Let's see what happens. Okay, it's now 9 o'clock in the morning, or it's Monday morning especially, or whatever it is, the workload just heated up. And so now we got a bunch more pages that are hot. In fact, we're kind of pushing the boundaries of what's in this guy, and there's a trend going on of things are getting hotter. Well, the algorithms can detect that kind of behavior and say, we better get another region ready to go. We better say, it's okay to allocate over there. And so then the memory allocation algorithm will start using that channel for new hot pages as they come in. Whenever there's an allocation, you can kind of assume in most cases it's going to be hot. Why else did they allocate it if they weren't going to use it? That's not always true, but it's a fair assumption until you can get some history. So after a little while, we get history on that page, then we really know how it's being used. But initial allocation, better play it safe and call it hot. So there we go. Now, after a while, maybe it's Friday at 5 o'clock or whatever. Maybe it's noon and everybody's out to lunch. Things are going to start to cool off. There's some pages that we can now label as cold because the history of that page, the accesses just aren't what they used to be. And so we can take this as an opportunity, back that guy back down to cold, make a little room over on power region 0, stick the hot pages back over there, and voila, we've got a cold channel. And we can take that guy down to a low power state by giving the hardware a hint. Turns out, even if you can't give the hardware a hint, the hardware is sometimes smart enough, or can be designed smart enough, just to detect the lack of activity on its own and drop down deep. But we really think there's a value add for the OS to tell it this information, because it doesn't know what the future looks like. It could be a momentary pause of coldness, if you will, versus the OS, if we're actively making it cold, we know those pages are really likely to stay cold, at least in the immediate future. So we view this as a necessary communication, but even hardware that can't take the hint, if it can detect this on its own, there's still benefit to be had. This is another, so I'm going to sort of show you the timeline as cooling occurs, but I want to take this opportunity to bring up a very important point about interleaving. So you may have already thought of this when looking at the chart that showed the power regions. If one were to interleave across those regions, it makes it impossible to cool, because moving a page, well, the page is resident on all the channels, so I can't move it. It's already everywhere. So it's okay to interleave still within a region. In fact, it's highly recommended, right? Interleaving can be a very good thing in terms of improving your throughput. But interleaving across power regions has to be disabled. So that's a potential perf hit, and we fully recognize that. And in some cases, and for some workloads, and I'll talk about this a little more later, that could be a reason not to do memory cooling, and that's fine. There are situations, like any other feature that's an optimization, there are situations where it works and situations where it's not so wise. We think there's lots of situations where it works, but just like balanced mode in CPU, if you're running some system that has to be, it's totally latency bound, it needs microseconds, right? Every little bit helps because you're doing stock trades. We don't tell anybody to go into balanced mode in that. You go high perf and you go flat out, right? Same thing. There are some workloads, probably not wise. So on the top, we've got, I guess you call it a traditional system, as it would be today. No memory cooling. Interleaving is going across all the regions. It's the normal system. On the bottom, I've got memory cooling enabled, which necessitates then that I've turned interleaving off. So let's see what happens. We got 8 power regions. So business as usual, things are going on, everything's busy. On the top, since it's interleaved, every channel is getting, of course, the same number of accesses. You're pulling pages off and putting full pages back in. On the bottom, since we've allocated in, I'll call it a clever way, that means that there's going to be some variation across the different channels, because we've taken all the non-page pool, for example, and we've put it on a subset of the channels. That's the only way we can then cool later on. So some of the channels will be hotter than others, and as long as you're not saturating, as long as you're not hitting a boundary where all of a sudden it's just hurting you in any significant way, this is cool, that's fine. And what that allows then is when the load does decrease and it's time to consider cooling, again, you're going to have a constant here, but here you've got guys that are kind of lightly loaded, if you will. And it turns out in this particular case, this is a real trace. This is not just sort of made up. In this particular case, there were a few channels where the data that was on those channels happened to be allocated in a big chunk and was no longer being accessed during the idle period. So the hardware, like I said, the hardware detected this to a certain degree and put it into somewhat of a low power state as a result, but not the deep one, just like one of the CKE kind of states. But there's still the channels that are clicking along. So after a little while, there we go, we decide, history is showing that we're entering an idle period. Let's go ahead and actively engage cooling. And so what's going to happen in that case is we're going to pick our hot channels, move all the hot stuff onto those channels, and everything else, the other 6, become very, very cold, icy cold, so that we can put them into a self-refresh state. What does that turn into? Well, the bottom line, of course, isn't whether I'm hot or cold, it's how much power am I saving. So this is the exact same scenario, busy, busy, busy. Things are now pretty much idle. Cooling kicks in, and as we move stuff and get it all lined up, power savings results. So do want to be clear. I don't want to overemphasize this, but I do want to be clear about the caveats. It's only fair. There are situations where your memory bandwidth bottlenecked. That's fine. Memory is the bottleneck of your system. You need every ounce out of it that you can, so turning off interleaving may hurt you. That's cool. If your workload is such that it's accessing all the pages all over the place and it's random, there's no partition between what's hot and what's cold, everything's lukewarm, again, what are we going to do about that? There's nothing we can do. Fine. Most workloads we don't think fall into that category, but if you happen to have one, fine. If your pages are constantly being repurposed, this isn't necessarily a killer, but it can make things difficult because the history we're keeping is inaccurate. Because we kept history of it being a data structure A, now it's a data structure B. We don't know that it changed. Our history becomes inaccurate, so that makes life difficult. Now, there are some things you can do about that if you're allocating and deallocating as part of this, rather than just sort of allocating it all up front, then moving it around. What you can do is use a LIFO rather than a FIFO scheme. That way, whatever pages you're not using, those will in fact get cold, because you aren't allocating and deallocating those at all. It's only the front of the queue that you keep throwing stuff on and taking stuff off. So if that's a scenario, you can still do some memory cooling in that environment. I'll talk a little bit more about the back-off algorithms. I'll just give you a couple scenarios. For example, if the system is very, very busy, not a good time to memory cool. If the system is completely idle, not a good time to memory cool, really, because what you really want to do is say, they're all cold, don't move anything, because that's just going to burn up power. Go deep, everybody, just go deep. If we see that we're cooling a channel, or we think we're cooling a channel, and the energy isn't changing, or it's not changing dramatically enough, back off. So we've got like 12 different scenarios. We're very careful to find everything we could that says, this is not the time, back off. And we've got multiple levels of back off as well. We can just stop moving stuff, or we can even stop tracking stuff and just basically we destroy our history at that point and have to regain it at some later point. But it means we're just like not in the code path at all. We're out of the way entirely in that case. So we think memory power is an important thing. It's showing up when we measure the component power of the system as a big factor in the pie chart. It's a good sized chunk of the pie chart. And with Windows 8, we've established this means of communicating with the hardware to jointly work together on reducing memory power. And it's working. It's giving us exactly the kind of return that we expected. We've done it on multiple workloads. We've done it on a couple different platforms. Pretty limited number of platforms at this point. But still, as soon as we have the next generation of platforms, we'll be all over it. And we're working with the hardware companies, our partners, to make sure that we can do this testing. Fine-tuning, there's still plenty of a fine-tuning, and we got time left. This is the standard thing we do on the processor stuff as well. As we get hardware, even as we're getting closer and closer to RTM, as we get hardware in, we can fine-tune, we can change the constants. And in working with our partners give us great feedback on this as well, because they're running on different workloads than we are, or different hardware than we are. And they say, you know, this isn't quite working well, or that isn't quite working well, and we can keep incorporating that in until it's too late, right? At some point, the door shuts and we can no longer make changes. But this kind of stuff, actually, the door stays open quite a while, because these don't require anything other than generally under constants to change in the system. And that's not super dangerous. I can get up there in the war room and I can argue for that stuff and usually get it through. Okay, I'm going to switch now into just a couple slides that are kind of advice to the developer, if you will. And it's not just memory management. I'm back to talking about the entire system. The goal is, don't wake sleeping dogs. There's no reason to wake something unless there's useful work to be done. There are too many situations, there's too much code out there that just constantly wakes up, checks to see if there's something to do. Nope, go back to sleep. They are waking stuff up all over the place. They're writing logs to the disk, even though the log entry consists of nothing happened over and over and over again. You're doing heartbeats constantly over the network. And 99.999% of the time, it's there. And so, did you really need to do it that often, that frequently? Can you not detect and back off in situations like that? So, event-driven, event-driven, event-driven. That's kind of the mantra that comes out of my team. And we're evangelizing that throughout our company and making sure that Windows Server 8 is going to have a lot less of that kind of unnecessary activity going on, so that the CPU, the memory, all the other components can get down low and stay low. There's usually a big advantage of having long idle periods rather than short idle periods. If you chop it up and you're constantly waking up and then go back to sleep, you can't go as deep because that exit latency is going to cost you more. What you want is get your work done, big idle period. Get your work done, big idle period. That works. That's a power saver. So as an example, in In previous releases, you could never get an idle period longer than 15.6 because that's our clock, and it's going off at least at that frequency, if not faster. In the next release, we have the capability of actually adjusting that, of skipping clock ticks, of doing things that actually can silence the system for hundreds of milliseconds at a time, if not longer. Right now, we're in that hundreds range in the best scenarios. Before, it was all less than 15.6. In fact, it was usually around the range of 1. That was your typical late idle period, was 1 millisecond at a time. So a lot of work went into this. One of my guys has worked on this full time, the entire release. The problem is this single frequent timer, right? One guy can destroy it for everybody. It doesn't matter if 10 people are waking up every millisecond or one person's waking it up every millisecond. The guy's killing you. So you have to watch out for legacy drivers, legacy hardware, legacy software. You have to go in and make sure you've cleaned up. And that's exactly what I'm going to talk about in the next slide. There are some tools I listed here, and we can talk about that offline if necessary. But there's documentation that does exist. And there's new stuff. This XPerf, the energy diag piece is new in this release to give a lot of information about where, for example, who are the things that are waking it up? What are the interrupts? What are the DPCs? What are the timers? Who is it that's bugging the CPU all the time in the middle of a Saturday when it really should be just sleeping? Did I miss? There it is. Did I miss a slide? Hygiene? Yeah. I did. I didn't. Did I go right past this slide? No. Okay. This one. Okay. Thank you. Sorry. I double-clicked at some point there. So the hygiene activity, I should have told you since that was the title, we call it hygiene because we want to clean up the house. And we cleaned up our own house first. We wanted to make sure that we weren't the ones that were waking up the system, the CPU, the memory, the disk, the network. We cleaned our house. Now we're evangelizing that everybody else needs to clean their house as well. We need to work together to make sure that we're getting the system idle and staying idle. So that's what we mean by hygiene. Okay, so in general, the kinds of things when you're developing code, whether it's drivers, applications, OS code, whatever, this is pretty straightforward stuff once you get in the mindset of trying to get things idle. You got to avoid the activity. You're polling, you're spinning, your idle loops, your timer wheels. Every time you wake up and do nothing, you just cost, right? That bought you absolutely nothing, and your energy bill went up, and now you're paying whoever it is, Puget Sound Energy, more than you needed to. Everything's got to be event-driven in order to really do this right. We have coalescible timers, and we put these APIs in the last release. We've added more for this release. If you've got a timer, can you give us a window? Can you say, wake me up in 5 seconds, but it's okay if it goes till 6, till 7, till 8, right? I'll give you 5 seconds plus 2 seconds of tolerance. That allows us to work, right? We can take 6 or 7 timers that were all within that window and collapse them down into one spot, wake up once, go deep. So very, very strongly suggest that if you can't go completely event-driven, you at least get coalescible timers into your act. Periodic disk and network activity. Like I said, if you're just constantly pinging, if you're constantly logging, and it's not doing anything for the user, well, you're just costing money. Optimizing code for performance is also often a win for power. If you reduce your code path, you've reduced your power in a lot of cases. So it doesn't have to be a perf versus power fight. Sometimes you can get both for the same piece of work. And for heaven's sakes, don't drop us below 15.6 or whatever we are. I mean, we've got software that has existed in the past where they drop us down to 1 millisecond by default. It's killing us. Okay, so kind of wrap up the pieces of what Sean was saying and what I was saying. Collaborative. We want the hardware and the software to work together. We're not in the business of trying to control everything. We want to develop these abstractions and have the hardware and the software talk to each other about performance and about power at a very useful level, not a twiddling the bits level. When the ACPI interface becomes available, jump all over it, make sure you understand it, talk to us if there's anything in there that you don't understand, or talk to anybody else who's on the ACPI committee. Absorb it very quickly so that you can then reflect that into your hardware, into your software. The logical processor idling is a good example of something. That's an ACPI 4.0, so you can do that now. There's no reason you can't be aggressive on that right now. Consider working with us on the memory cooling aspect. We are working with partners, and we want to continue to work with partners to figure out how to fine-tune this, whether or not we want to make it a default or a default on some systems. The OEMs can choose to ship systems. Oh, it's right here. Okay, I don't know what happened there. Oh, best practices. So like I said over and over again, event-driven design, idle equals quiet. I mean quiet, quiet, quiet. There is some sessions. I believe one of them was the previous. I think the bottom one, I think, has yet to come. Either I got it reversed, but I think that was what it said. I think this one's already been by and this one's yet to come. There is online documentation. You can come talk to Sean and I afterwards and hunt us down. That's no problem. There are things we can do together. There's lots of stuff we've been through. And there's just lots of opportunity here to save money. You save money, you go green, and you look good. You save polar bears. It's just all good, right? I go home and I tell my wife, I saved polar bears today. She gets a kick out of it, but such is life. Okay. Thanks again for coming. This has been fun, at least it is for us. We're very passionate about this topic. It's something that we eat and breathe every single day. So if there's Q&A, by all means, you can ask us now or ask us later. There's a mic up there if anybody wants to. Hey, that's fine. Come talk to us later if something comes to mind, and thanks again for coming.